Assalamualaikum and good morning. My name is Amir Afif Praji Ben Jamsari from ELK3. So I will answer the question A from the assignment 1. So from the transfer function given, we need to change the transfer function into the standard form. So for the j omega plus 2, we can factorize 2, it will be 2 j omega over 2 plus 1. And for j omega plus 10, we factorize 10, will be j omega 10 plus 1. So we insert back into the equation, it will be 5 times 2 j omega over 2 plus 1 over j omega times 10 times j omega over 10 plus 1. So we can simplify 5 times 2 is 10 divided by 10, it will be 1. So the final answer will be 1 j omega over 2 plus 1 over j omega over 10 plus 1. So from the transfer function, we can change into the decimal transfer function. It will be 20 log 1 plus 20 log j omega over 2 plus 1 minus 20 log 1 over j omega minus 20 log 1 over j omega over 10 plus 1. So from this equation, we can get 4 lines. Line number 1 is 20 log 1 as gain line. Line number 2 is 20 log j omega over 2 plus 1 as simple zero line. And line number 3 is negative 20 log 1 over j omega as pole at origin. And then number 4 is negative 20 log 1 over j omega over 10 plus 1 as simple pole line. Now for the magnitude graph. So we know we have 4 lines. So line number 1 is the gain line. This one is the gain line, 20 log 1. We use calculator, we will get 0 dB. So line number 2 is this one. This one is 20 log j omega over 2 plus 1. So as we know from the table, it will be start at z and end at 10 z at positive 20 dB. So z here is 2, so 2 until 20. So the line will be start at 2 and then at 20 kilohertz at 20 dB. So for the third line is this one is the third line, 20 log 1 over j omega. So from the table, we know that it will be start at 1 at 0 dB and will be end at 10 at negative 20 dB. So it will be start at 1 and end at negative 20 dB at 10 kilohertz. So the fault line is this one. This one is the fault line. It's 20 log 1 over j omega over 10 plus 1. So as we know from the table, it will be start at P and end at 10P. So P here is 10. So it will be start at 10 and will be end at 100. So the line will be start at 10 and will be end at 100 at negative 20 dB. Now to both plot, we need to find the point. So at 0.1 kilohertz, there are 2 lines. Line number 1 is 0 dB and line number 2 is positive 20 dB. So the point will be at 20 dB. So this is the point. So at 1 kilohertz also have two lines. Line number 1 is 0 dB and line number 2 is 0 dB also. So the point will be at 0 dB. So this is the point at 0 dB. So for the third line at 2 kilohertz, there are three lines. Line number 1 is 0 dB, line number 2 is 0 dB, and line number 3 is negative 6 dB. So the point will be at negative 6 dB. This is the point at negative 6 dB. So for at 10 kilohertz, there are three lines. Line number 1 is 0 dB, and number 2 is positive 14 dB, and line number 3 is negative 20 dB. So the point will be at negative 6 dB. So the point will be at negative 6 dB. This is the point at negative 6 dB. So at 20 kilohertz, there are three lines. Line number 1 is negative 6 dB, line number 2 is positive 20 dB, and line number 3 is negative 26 dB. So the point will be at negative 12 dB. So negative 12 dB, it will be here, negative 12 dB. So for the sixth line is at 100 kilohertz. There are three lines also. Line number 1 is negative 20 dB, and number 2 is positive 34 dB, and line number 3 is negative 40 dB. So the point will be at negative 26 dB. So the point will be at negative 26 dB. So to plot, we start from the here and straight line until 1 kilohertz at 0 dB, and the line will be continue until 2 at negative 6 dB. So at 2 kilohertz, it will be straight line from 2 kilohertz until 10 kilohertz at negative 6 dB. So straight line from 2 kilohertz until 10 kilohertz at negative 6 dB. So from 10 kilohertz to 20 kilohertz, it will be go down at negative 12 dB. So from 10 kilohertz, it will be go down until negative 12 dB straight line. So from negative 20 dB, it will be go down to 100 kilohertz at negative 26 dB. So it will be straight line at 26 dB, and the line will be straight. Okay, now for the phase graph to plot. So line number 1 is the gain. This one is gain 20 log 1 equal to 0 degree at the x-axis. So for the line 2 is this one. This one is 20 log j omega over 2 plus 1. As we know at the table, it will be start at z over 10 until 10z. So z here is 2, so z over 10 is equal to 0.2, and it will be end at 20. So the line will start at 0.2 and end at 20 at positive 80 degree and straight line. So for the third line is 20 log 1 over j omega. So from the table we know if the line is 1 over j omega, it will be straight line at negative 90 degree. So for the fourth line is this one, 20 log 1 over j omega over 10 plus 1. So as we know, the line will be start at p over 10 and will be end at 10p. So p here is 10, so p over 10 is 1 and it will be end at 100. So the line will be start at 1 and end at 100 at negative 90 degree, and it will be straight line at negative 90 degree. Okay, now we want to plot. So at 0.2 kilohertz, now there are two line. Line number 1 is 0 degree, line number 2 is negative 90 degree. So the point will be at negative 90 degree. So this is the point, negative 90 degree. So second one is at 1 kilohertz. So at 1 kilohertz there are three line. Line number 1 is 0 degree, line number 2 is positive 30 degree, and line number 3 is negative 90 degree. So the point will be at negative 60 degree. So the point will be at negative 60 dB. This is negative 60 dB. So at 20 kilohertz, there are three line also. So the line number 1 is negative 60 dB, 60 degree, and number 2 is negative positive 90 degree, and line number 3 is negative 90 degree. So the point will be at negative 90 degree. So the fourth line is at 100 kilohertz. At 100 kilohertz, there are three line also. Line number 1 is negative 90 degree, and number 2 is positive 90 degree, and number 3 is negative 90 degree. So point will be at negative 90 degree. So now we want to plot. So the first line will be start at negative 90 degree until 0.2 kilohertz at negative 90 degree, straight line. So from here, from 0.2, it will be up until negative 60 dB from 0.2 kilohertz to 1 kilohertz. So straight line from 0.2 kilohertz until 1 kilohertz at negative 60 degree. So from 1 kilohertz at negative 60 degree, so at 20 kilohertz it will be also at negative 60 degree. So 1 to 20 kilohertz will be straight line at negative 60 degree. So from negative 60 degree at 100 kilohertz at negative 60 dB will be down at negative 90 degree. So at 20 is negative 60 degree, and at 100 is negative 90 degree. So straight line. So from 100 kilohertz it will be maintained straight at negative 90 degree. This is enough for me for the explanation for the question A. My friend will be continue the question B. Thank you.
Hi, my name is Wong Hui Yong from BELK3. Today I would like to explain Advanced Circuit Assignment 1, Question 1b. For this question, we are given a Bode magnitude plot and we are asked to obtain transfer function S that correspondent to it. First, I will identify the corner frequency from the Bode plot. From the graph, we can clearly see that the slope changed at 5 radius, 10 radius, and 100 radius per second. So the corner frequency are 5, 10, and 100 radius per second. Now I will analyze each corner frequency one by one. First corner frequency. At omega equal 5, the slope increased by plus 20 dB per decade. This means we have 1 0 at W equals 5. So the corresponding term in is 1 plus S over 5. Second corner frequency. At omega equal 10, the slope decreased by minus 20 dB per decade. The integrated one pole at W omega equals 10. So the term is 1 plus S over 10 in the denominator. Third corner frequency. At equal 100, the slope decreased again by minus 40 dB per decade. Since minus 40 dB per decade means 2 poles, we write in this as 1 plus S over 100 square. Step 3. Write the transfer function structure. Hs equal to k multiplied by 1 plus S over 5 divided by the pole terms 1 plus S over 10 and 1 plus S over 100 square. So we have Hs equal to 1 plus S over 5 over 1 plus S over 10 times 1 plus S over 100 square. Step 4. Determine gain constant K. From the plot, the low frequency magnitude is 20 dB. Using the formula, 20 equals 20 log base 10 of K. Dividing both sides by 20, log K equals 1. So K equal to 10. Now I substitute K equals 10 into the transfer function. Hs 10 times 1 plus S over 5 over 1 plus S over 10 times 1 plus S over 100 square. And this will be a standard Bode form. Next, I will convert this into a polynomial form. First, rewrite each of the term. 1 plus S over 5 equal to S plus 5 over 5, and 1 plus S over 10 equal to S plus 10 over 10, and 1 plus S over 100 equal to S plus 100 over 100. Now, I substitute everything back into the Hs and simplify. After simplify the constant, the final transfer function becomes this. So 200,000 times S plus 5 over S plus 10 times S plus 100 square will be the polynomial form. So this will be the standard Bode form, and this will be the polynomial form.
Mathematical representation of the relationship between the input and output of linear time variant (LTI) system in the Laplace domain. It is defined as the ratio of the Laplace transform of the output to the Laplace transform of the input assuming zero initial condition. We have the two plot for the transfer function is transfer function to Bode plot and Bode plot to transfer function. Now we're looking for the definition for the transfer function to Bode plot. Transfer function to Bode plot defined as the ratio of the Laplace transform of the output, the Laplace transform of the input of all linear time invariant LTI system assuming zero initial condition. Bode plot to transfer function is referred to the process of determining or estimating the transfer function of a system from its Bode plot by analyzing the magnitude and phase characteristic of the plot. Now we want to key feeder of the transfer function. We have to pole and 0. Value of the SS make the numerator 0. Pole value of the SS that make the denominator 0. System order. The order of the system is high power is in the denominator. High order system are generally more complex and slower to analyze. A system is the stable of the whole pole line in left half of the S-plane. Pole on the right half of the imaginary axis may cause neutrality frequency response. By replacing with the JWJ omega W transfer function provide the frequency response of the system. This is used to generate Bode plot, Linguist plot, and Nicholas chart. Gain of the system. Gain of the system is the transfer function include the gain factor, which indicates how much the input signal is amplified, attenuated. Now we go into conclusion. In conclusion, we understand that the transfer function is very important concept in control system because it clearly shows how system output respond to given input. It helps in analyzing system behavior without focusing on internal physical detail. By studying the transfer function, we learn how poles and zero affect stability, how system order influences response, and how frequency domain to like Bode plot and derivative. Overall, learning about transfer function has improved our understanding of system analysis and made complex system easier to study and design in the systematic way. Thank you.